Hello viewers, welcome back to the channel. I hope you are doing good. Today we are going to look into an important data structure called heap, and there is no internal implementation of heap in JavaScript, so we will have to implement our own version. So what is heap? Heap is a tree-like data structure and it is used to get us the values in the faster manner. Like let's say if somebody comes to us and ask about give me the minimum number out of some numbers in O of one time or maximum number out of some numbers of one time, or maybe there are some tasks and every task have some priorities assigned to it, and somebody asks us, okay, give me the one which is having the highest priority. So in those cases we need to use heap, and there are like some common examples like job scheduling, even the graph algorithm, and I mean wherever we have to do something which is based on some criteria and we have to find the processes or anything in faster manner, we have to use heap. So okay, let's try to understand it. But before actually understanding how we are going to implement heap, first try to understand why we need heap. Why can't we use an existing data structure, maybe array, for an example? So here in this example I have some of the tasks given A, B, C, E, D, and they have some priorities assigned to it. So for an example here, if we see, we have E, task E, which is having the priority 1, means it is the task which is having the most priority. The lesser the value, it is of the highest importance. So importance of this task is higher. It can be opposite as well, but here will be trying to understand, okay, 1 means we want it first. Then comes the 2, then it will be 3, and then it will be 4, then it will be 5. So this is how the priorities of this task would be. Now what all things we can do out of this task? There are some things like somebody can come and ask me, give me the task which is having the highest priority. Now I'm going to store it in the array. Let's say I've stored it in the array like this in the sorted manner. Now what happens? I for finding the task which is having the lower priority, I mean the highest priority, I have to go through each of the tasks one by one and then get the one which is having the lower priority. I sorry, the higher priority. So it's gonna take me O of n time in doing so. But that is not efficient, right? We want it faster. As I explained, he gives us the values, whatever is suiting to our condition, max, min, or whatever it is, that gives us in O of one time in the faster manner. So data retrieval is faster using heap, but array. If I have to use array, it's giving me the values in O of n time. So maybe some of you might think, okay, why are you keeping values in unsorted manner? Why can't you use it? Why can't you keep it in the sorted manner? Then it will be easier for us to get the values. We can do that. So if we sort this based on the priorities, so E will come first, then it will be C, then it will be A, then it will be D, and then it will be B, sorry, B, right? Now if somebody comes and asks us, okay, give me the one which is having the highest priority. So I'll just go and see the first one in my array and I will give it in O of one time. Awesome. But thing is, data retrieval is faster, but the thing is, like, let's say if new task arrives, let's say called G, and it has its own priority of 6. Now I have to find the suitable position of this in this array, right? So I need to go through it, the position, and then find the suitable position of it, and then I have to shift the other element to make a way for this element to sit at its position, and this operation will take me O of n time. But I don't want that. That's like too much, because in the worst scenario it might be case that I might have to shift each of the elements. C will go here, D will go here, and B will go here, right? Basically literally everything is getting shifted, and that is why it will take O of n time. So we understood that, okay, even if we keep data in sorted manner in an array, while we'll have to update, or while we'll have to insert. So basically insert, update, and delete, all these operation will take us O of n time if we are going to store it in array. Heap can also be two kind. It can be either min heap or it can be either max heap. So min heap is something where we can keep. So basically, as I explained, heap is a tree-like data structure. So we store values like this. There will be a root, and then it will have its children, left children and right children. We are going to study binary heap, so where there will be two children, right? We are going to study, there can be many different kind of heap, an array heap, and there are a lot of different kind of heap, but we are going to study binary heap. Binary heap, there will be a root, and it will have its left children and the right children. Since it's a min heap, so here the root of the node, or the root or the parent, we can call it as parent will be smaller than the its children. So here one, this node should be smaller than both of it. So this is satisfying the min heap condition. About if we see this node, this is also following or honoring the heap condition. This is lesser than these two, this is lesser than these two, and this is lesser than these two. So this is what min heap is, and root is something which is the smallest element. If somebody comes and try to get the smallest element out of min heap, it can just get the top value of it, and it can get it in O of n time. Sorry, O of 1 time. Similarly, we have a max heap where the condition is the root value or the node, the parent value will be more than the both of its children. So here you can see that the root is 8 and the children are 7 and 6, which is less than the 8. Similarly, 7 is more than 5 and 4, 6 is more than 2 and 3, 5 is more than 0 and 1. So we can see that every node is satisfying the max heap condition. So here the root is the greatest element. So what are the conditions of binary heap? So basically binary heap is a tree which should be complete. I mean the complete binary tree. If you don't know, complete binary tree is a tree where every level. So basically in a tree, if we see, there are multiple levels. This is first level, second level, third level, and the fourth level. Every level should be completely filled. If you see and follow from this example, first level is having only one node, second level is having two nodes, and this is completely filled. There is no place where we can keep another node, right? At the third level also, you see every place are filled. There is no incomplete level or incomplete node here, or something which is left out. There is no null. If we had we did not have this, right, in this case it would have been empty node, so this level would have one element less. So that's not the case here, right? So I will just write it back. So, and this is about the level should be filled, and the second thing is all it nodes should be as far to left as possible. So you can see that, okay, that's fine. Like first of all, the all nodes should be, all levels should be filled. But if it is not filled, at the example here, you can see that this last level is not completely filled. We could have some nodes here as well, which we did not, which are not present, right? So in this case, we can still consider it as a binary heap, because the nodes which are there, which are the incomplete, are as far left as possible. All the nodes in the last level are at the extreme left, right? So this is an important condition of binary heap. Another important thing is we are going to use array to store the values as tree is complete binary tree. Reason is due to its efficiently in handling the data. So since it's a binary heap and every level is completely filled, so we are sure that array will not have empty spaces in between. And also, let's say even the last level is not filled, all the values are to the extreme left, right? So that means the array will be completely filled and there won't be any memory wastage. So that's why it will be able to efficiently handle the data. Another very important thing is we have to find the child and the parent, right? If I'm at index I and I want to know about my child, like left child and right child, array will help us in finding it very easily. Also, let's say I'm a child and I want to know about my parent, and I'm at node I and I want to know about my parent, I can again easily find out my parent. So array will give us a relationship that will be very helpful in finding those. So let's say I'm at node index I and I want to know about my left child. So that will be 2i plus 1. And if and I want to know about my right child, that will be 2i plus 2. Similarly, if I want to know about my parent index and I am in at index I, then I can do I minus 1 divide by 2, and we have to just do the math dot floor. We can easily find out our parent index. So you can see that by using array, first of all, we are able to efficiently store all of the values. Second thing is we can easily find out the our relatives, like child can find their parent and parent can easily find out their children's, and they can do it in O of 1 time, because you know, if you know the index in array, it will just takes you O of 1 time to get the values. So that's why we are going to use array instead of a tree kind of structure in representation, like tree class or something. Okay. So next we are going to discuss about what all operations we can do it in the heap. So heap can perform some operation. First is Enqueue and Dequeue. So Enqueue is basically keeping the data, putting the data. You can think of it as like push, what we do in an array, right? If we want to push a new data, we do Enqueue. Similarly, Dequeue is something where we remove the data. So it is equivalent to pop while we want to remove the data from the heap. So Enqueue basically removes the top element. So this top element can be min or max based on whether it's a min heap or it's a max heap, right? And the third thing is peak, peak or top. In some implementation they call it as top, some implementation they call it as peak. So this is basically something which gives us the first value, the top value, or the whatever we see at the top of our either min or max. If it is a min heap, this will be the minimum value. If it is a max heap, this will be the maximum value. So this is what it is. And all of these operations will be performed in log n time. So for an example, let's say I have this heap given. What is this? This is a min heap. This is a min heap. And now you can see that every element, every child is greater than its parent. So that's why it's a min heap. And let's say if a new element arrives, we don't have six, right? Let's say we just try to put, or maybe four. If a new element comes, and we will keep it at the end. So whenever a new, so we are trying to discuss the Enqueue. So Enqueue we are trying to put the new value. So we will put the value at the end. So first value will come at the end, and now we have to maintain the heap property at each of the node. So here we can see that the new element which has come, it is lesser than the root. But since it's a min heap, it's a min heap. So this should have been, it should have been opposite. 4 should have been here and 12 should have been here, because root can't be more than its children, right? So to maintain the heap property, whatever the new element has come, that will be swapped with this value. So now 4 will come here and 12 will go here. Now again we'll see whether the new property which has come, sorry, the new element which has come here, is it obeying, sorry, it is obeying our property, heap property here. So we'll compare with the parent. So here if we compare with the parent, we can find, okay, the parent itself is more than this, but parent should have been lesser than this, right? Because it's a min heap. So again, we need to swap the values. 4 will come here and 7. So it is again it again needed to swap the value. So we have swapped the value. Now at every place, every node is following the heap property. So we have successfully inserted the new data, and you can see that while we talk about the time complexity of this operation, so we literally had to do one operation at each of the levels. So basically, how many levels we have, that many operations we have done, right? So we had 1 2 3 4. So basically we have done 4 operations. So total number of nodes, how many total number of nodes we have here? If we count, we have like 16 nodes in total, and we have 4 levels. So 2 raised to the power 4 is equal to 16. So those many levels we have. 2 raised to the power n is equal to total nodes, and these many levels we have n levels, and we have done n operations. So if we take log, so this comes as a log n. So basically the time taken here is log n, is the total nodes. So Dequeue is like removing the top element. So let's say we need to remove the top element from here. So 4 will be removed. So but we can't directly remove the 4, like that's the root of the tree, right? So we can't just go and remove it, like tree will be broken. We basically swap the last value from the top value, and then we pop out the last value. So what will happen in this case is this 12 will go here and this 4 will come here. So first the swap will be done. After swapping the values, we will remove the last element, because that's what actually we wanted to pop it out, right? So we pop the last element. But at the result of this operation of swapping, we have we have got a new element at the root. So now we need to check whether it is following the heap property. Okay, so we can see it's a min heap, and here the root value is 12 and the childrens are less than this. So basically it is not following the heap property, so we need to swap it with the lowest value. So we can see that the lowest value here is 5, so we'll be swapping this 12 with the 5. So 12 will come here and 5 will go here. We'll again check here whether it is following the rules. Now we'll check again here at this level, because now 12 has come here. So we'll check whether this is following the heap property at this level. So we can see that 12, because it's a min heap, root should be less than its children, but this is not following that property. So again, we need to swap it with the smallest value. So we will swap it with this. So 7 will come here and 12 will go here. So now we are seeing that it is following the heap property. So in Dequeue also, what we have done, we have went down from up, right? So we call it as bubble down. And in where we have explained, like before we have explained Enqueue, we try to value at the last and then we try to push it to the top. In Enqueue we do bubble up, that is bubble up, or sometime people call it as heapify up. And this operation some people call it as heapify down, or some people call it as bubble down, right? So in Dequeue we come down, and in Enqueue we come up from the root, from the leaf to we go to root in Enqueue. And in Dequeue we go opposite, we come from root to the leaf node, and we'll try to maintain the heap property at each of the parts. So let's implement this. So we need to create a heap class. It will have its constructor. Constructor will take the comparator function. We will call it as compare function. So we'll store it in our class. And let's say we don't have comparator function given when we instantiate. So default value we have to create. So by default we'll create a min heap function where we will have to give, sorry, this should be a minus b, and here it should be a minus b. Okay, awesome. So this is the default value, and then we will need the heap. So heap would be an array as we discussed before. Now we'll write some parent-child relationship functions. So first is get parent index. So here we'll pass one index, we'll just call it as I, and we will return the map.floor of I minus 1 divided by 0. Similarly, similar to the parent index, we need two more functions, which should be get left child, that should be 2 into I plus 1, and similar to this, we can have get right child, that would be 2 into I plus 2. Also, we can create a swap function where we will be given two indexes which we need to swap. So we'll take the benefit from the ES6 syntax. So this dot heap at the value of I needs to be swapped with this dot heap at the value of j. This will be swapped with I will j, right? So here I will come. Now we need more functions, right? So yeah, parent-child relationship is fine. Another thing is we'll be swapping at various places wherever we'll find that it is needed or not. I mean, if there is a violation of the heap property, we'll need to swap the values, right? So we'll write a function swap needed, and this guy will take the parent index and the child index, and this gonna run the compare function. Compare function will take the value at the parent and child, so the parent index and the child index, that will be this, and then okay, this needs array. Okay, so swap needed, and this guy will be returning positive or negative values, right? Either it will return as the positive or negative values. So we'll see what we need. So first take an example of the min yeah, what do we call it? Heap, min heap, sorry, min heap. So in min heap, we have a minus b. A is parent and b is the child. A should be less, right? A should be less. Parent should be less than, like this. Let's say if this is the example of the min heap, parent, the parent node should be less than the child node, right? And parent is a here because we are passing the parent index here. That should be less than here. So if there is no violation, then it would give us the negative values, right? It would give us the negative values. But if there is a violation, then it will give us the positive value, right? So we need to take the violation. Swap will be needed whenever it is a violation. So this works fine for min heap. Also, this will work fine for max heap. In max heap, we do b minus a, and in this case, condition is opposite. We need child as greater than the children, right? So let's say here if we have 8, that is greater value, and all of these are small, so that satisfies the max heap condition. So means a is greater, and here the max if condition will be b minus a, and we know that a is greater, so b minus a will be negative for the max if condition, for max if to be valid when we don't need the swap. So in both of the condition, negative means valid case, and positive means invalid case, and whenever it's an invalid case, we need to swap. Now we have to write the peak function. So peak can be a get function. So we'll just write peak, and we have to return the top value. So top value will come from the 0th index at the heap, right? And again, we will write another function called size, because we might be needing the size of the heap so many times. So it's better we create one function for that. So the it would be heap dot length. This is going to be the size of it. Now we'll start with our Enqueue function. Enqueue will take a value, right? Enqueue is gonna take a value, and we need to put it at the end. We will put it at the end. Let's say we'll put it here, right? At the end of the list. So now we need to see that after putting this up, whether it is satisfies the heap condition or not. So we need to compare it with the parent, and if it doesn't satisfy, then it will go up. It will take the place of the parent. Like if I have the node here, then it will go up if it doesn't satisfy. If swap will be needed, right? So it will keep on going up and up. But what will happen, will push the value. So we'll directly go to the heap and push the value. So new value has come at the end, right? The new value has come at the end, but we need to see whether this is fine or not. And if it is not fine, this need to be swapped with the parent, and this should go up and up. So for that, we are going to create another function, that is bubble up. I've already discussed about it, and bubble up will be starting at this position, which is the last position. So whatever is the heap length, from there it's going to start. This is the last index where my new value is. So from there we need to keep on doing this bubbling up. Implement the bubble up function. So bubble up, we can just copy this skeleton. We'll keep this bubble up here. Bubble up will take an index, and we know that we have to go up and up, and we have to continuously keep comparing with the parent. So for continuously doing some work, we need a loop. So we have taken a while loop. Now I need to get my parent index. So I will get my parent index using the function of get parent index. Now I got the parent, so I need to compare with the parent, right? So but before comparing with the parent, I need to check whether wherever I am, is it a correct position or not. I mean, we should not go out of bound, because we are going up and up and up, but we can't go beyond a certain point. We can go till the last position, till the last index. I mean, till the first index. The first index means the 0th index. So we should be greater. If we want to perform more operations, we should be at the higher index than the 0th index. Beside, we need, oh, sorry, I forgot that we already created a function for that. So we'll give the parent index here and our index here. So if there is a violation, this will return us the true. And if there is a violation, we need to call the swap function, and we need to pass the parent index and this index, right? And we will swap the values. But now we have come here, right? We were here, and now we have come here. So at this position again, we have to perform the same task. And what will be the new index? The new index will be my current parent index, right? So that's why in place of index, I will update it with the parent index, because now at the parent index also, what was my last parent index? Now at that position, I need to perform this activity again and check. And if this condition is not passing, I mean there is no violation and we have reached at the top of the heap. So then we can just return. So now bubble up is complete and enqueue is also complete. So now we will write the dequeue function. So dequeue function, as you know, what happens, it again takes a index. Sorry, it doesn't take an index. Sorry, it doesn't take an index, and it basically removes the top element. But we can't directly go and remove the top element. We need to swap it with the last element. So first of all, we'll take the top element and we'll see, okay, peak is a getter function, so we no need to call it. So now we got the top element. After getting the top element, we will swap with the last position. So swapping will be done from the 0th position to the last position. So we have a size function that is again a getter, so no need to call it. And basically this will give the index size minus 1. So we need to swap. So now my top value went at the last, which I can remove. So I can just go to heap and I can just remove it. That is fine. But I need to make sure that the last value which has the last value which I have kept at the first position at the 0th index, that should satisfy my heap, right? So I need to keep checking that with my children, because right now at the root I've introduced a new element which might not be the correct position of that node, right? So that needs to be checked with the children. So we need to find the children and we need to find the correct index of the children with which we will swap it, right? And then we'll keep it doing and we'll reach at till we reach at the end of the index, I mean end of the heap. So for that we will be creating another function called bubble down, because we are going down, and we will pass the index 0. Now let's, okay, before returning from here we need to return the top, because that's what we need to return from the dequeue function. Okay, now let's create bubble down. Bubble down takes a index, and now again here we will have to do something continuously, because we will be keep checking the root with its children, then this root to its children. So we have to keep on doing something, right? That's why we need a while loop. And now we need left child, that is, and we'll pass the index. We'll perform the same thing and we'll get the right child. And before doing all this, we will store the current, we'll store the index in the current index, or we'll call it as min index, or maybe swap index. So initially we will just consider this index as the swap index. Now we'll keep on checking with the childs whether swap index should be something which should be either of the child, right? But before that we need to check whether this left child is within the range, because we are going down and down and down. So we need to be just before the length. So okay, first let's get the size here. Size would be uh, size, this dot size, and here we can give that our left child should be less than, that should be less than the size, right? That should not go beyond it, because we are coming from up. And beside that we need to do the compare function, and we need to see for the violation, right? I hope here I have called, okay, we don't have compare function, we have swap needed function, right? So swap needed function will pass the our index, that is the this index here, or maybe we'll pass the swap index and we'll pass the left child, because we are doing it for left child. And if we find, okay, there is a violation, then we can make swap index as the left child, because left child should come in place of parent. And we never know, there might be a case where right child can also fall into swap index, right? So we need to perform the same thing with the right child as well. So now at the end of this, if my swap index get changed, my swap index is no longer is equal to my index, that means we need a swap actually, right? So we are calling swap and we will pass we have to swap between swap index and the current index, right? And now the new index will be the swap index, whatever is the swap index right now, because we have come down, like from here, from this position we might have come here, right? So earlier my index value was this, but now my index value will be this, and we will perform the same operation here. That's why I'm updating the index value. But let's say this condition is not true. So app index is still the index. Both are the same value still. That means there is no violation. Everything is fine. My index, this index is already at its correct position. So I can just return from it. We don't have to do anything, right? So we have implemented Enqueue and Dequeue and peak, all the functions we have implemented. So let's run it. So for that, let's say now we have created an instance of heap class and we are enqueuing some values, and initially we are trying to see the top value. So top value initially will give the min value, because by default we are not passing any comparator function here. So it's a min heap, right? So min heap, it will give us the smallest value, that will be the 1, and then after dequeuing it, we'll get the second highest value, right? Because first is already removed from the list, right? So first is not the first value, like the one value. The one is not present in the list in the heap. So the next smallest value will be the 5. So this will be printing 5. So let's run it and see if it works. So this is throwing some error. Looks like peak is a getter function, so we should not call it. Let's run it again, and we are getting the values perfectly fine. So this is working nicely. If instead of this we can make it as max heap as well, now we can pass the max heap function. Now let's run it and see what is the values. So let's run it again and see what are the values now. So right now it's printing 9 and 7. So initially the big value among these are 9, and then we have removed 9. So the next is greater will be the 7. So that's why we are getting the 7. So I hope you have understood the problem completely. I'll be putting this in the solution and will be sharing my GitHub link for this, and will be solving some more questions using heap, and will be using this code directly. So please go through it again and try to write it yourself to get more understanding of it. Try to dry run it and you'll get the more understanding. I tried to explain everything as simpler as possible, but still you can dry run it, you'll get most out of it. Thanks a lot for watching my video, and I hope you will hit the like button and you'll subscribe the channel too. Thank you. See you in the next video.